Suppose you are interested in answering some kind of question using statistics, and you go out and you gather a bunch of data. After gathering all this data, you have to decide what to do with it. How are you going to analyze it? What are the best ways to show people the data you collected? And so the first thing we are going to learn in this class is what to do with data once you've collected it, a little bit about how to analyze it and how to represent it. So first we need to know some vocabulary. So raw data that's what we call the numbers and labels that you collect on individual subjects. For example, this could include things like the height of your subject, the weight of your subject, the gender of your subject. They do not need to actually be numbers, they could be categories. A variable is a characteristic that can differ from one individual to the next. Now, a single individual entity in your study, that is called an observational unit. Those may be people or animals, but they could also be things like states or schools or lots of different entities. Now, the sample size is the total number of observational units, and in this class it's almost always denoted by the lowercase letter n. So the number of observational units you have is denoted by n, and your data set is your complete set of raw data. Now, usually you want to deduce something about a large group of people, but looking at that entire group of people is not a reasonable thing to do because it's too time-consuming, complicated, or expensive. So a sample is a subset of your population, as in a chunk out of that population. So a subset of population versus a population that is the whole collection of subjects of interest. When data is taken from a subset, that's called sample data. When data is taken from the entire population, that is called population data. I mean, for example, this would be data taken from a census. And the census attempts to, at least, talk to everybody in the population. When you compute a summary measure, like an average, for example, from sample data, this is called a statistic. And when you compute that summary measure from the entire population, that is called a parameter. And there's a little bit of alliteration going on there. You get a statistic from your sample. You get a parameter from your population. So hopefully that would help you remember which is which. So the big question is how do you make sense of information that you have in your data sets? And can you use this information from the sample to draw conclusions about some population? And the general goal is to understand your whole population. As collecting data for everybody is too hard and expensive, you can use statistics to make an estimated guess about your population. So that's the basic idea, is you use a statistic obtained from sample data to estimate a parameter. And this works if you have something called a representative sample. For example, you might want to determine what proportion of eligible voters are going to vote Democratic in the next election. To estimate that, you're obviously not going to be able to ask every single possible voter. You'll take a sample, and you have to take that sample where people are from lots of different places, so you don't just poll, say, everybody at a university or everybody in a very small town, because those places might have lots of people that feel the same way. So suppose a sociologist assembles a data set consisting of the poverty rate, per capita income, serious crime rate, and teen birth rate for the 50 states in the US. First question, how many variables are in this data set? So how many different things are measured? So if you count them up, they measure the poverty rate, per capita income, serious crime rate, and teen birth rate. So that gives us 4 different variables. What is an observational unit? So what are the things we're collecting these variables or data on? Well, we are collecting the data about these 50 states. So an observational unit is a state in the US. And what is the sample size, as in how many states do we collect data for? Well, that would be n equals 50. In each situation, explain whether it would be more appropriate to treat the observed data as a sample from a larger population or as data from the whole population. So an instructor surveys all the students in the class to determine whether students would prefer a take-home exam or an in-class exam. Now, a lot of this depends on the context. If it's the whole group you're interested in, it's the whole population. So since this instructor surveys all the students in the class, we can pretty safely say that is the whole population. I guess we have to assume that this person does not have an additional class that they're trying to also do this with. Next, we have the Gallup organization polls 1,000 individuals to examine the percent of American adults who approve of the president's job performance. Now, they're trying to estimate the percent of all American adults, and they didn't ask every single American adult, they just asked 1,000 of them. In that case, this is a sample. Now, for each of the following statistical summaries, explain whether it is a population parameter or a sample statistic. In the 2000 census of the United States, it was determined that the average household size was 2.59 persons per household. Now, since this was a census, we can assume it was the whole population. So in that case, this is a population parameter. To estimate the average normal body temperature of all adults, a doctor measures the temperatures of 100 healthy adults. The average temperature for that group was 98.2 degrees Fahrenheit. So since we're trying to estimate the average temperature of all adults using a subset, that means that this is a sample statistic. And a question we'll learn to answer later in this class is, as this number is smaller than 98.6 degrees, which is kind of what we take as being the healthy average temperature, is there reason to suspect that that 98.6 is actually set a bit high? So we will do some data analysis later in this class to answer that question. We also need to know some names for different kinds of variables. So a variable that is a group or category name, each individual falls into exactly one category. That is something called a categorical variable. For example, gender, eye color, things like that. A type of categorical variable that has ordered categories is called an ordinal variable. For example, some kind of rating system where you do something like agree, don't care, disagree, like the things you do in course evaluations is an example of an ordinal variable. So course evals, things like strongly agree, agree, in the middle, disagree, or strongly disagree. There is some kind of order you can impose on those variables. A variable that has numerical measurements or counts, that is called a quantitative variable. And a variable is called continuous if every value in some interval is possible. Example of continuous variables are things like heights, weights, stuff like that. Technically, you can weigh 142.789231.864 pounds, but we don't actually, scales don't measure that accurately. So we treat them a bit as if you can't be something other than 140 or 141 pounds, but it is actually theoretically possible to have some value in the middle that's lots of digits of significance. So for each of the following variables, indicate whether the variable is categorical or quantitative. So the importance of religion to a respondent, were they rated as very, somewhat, or not. So this is an example of a categorical variable. And it's all the question asks you to answer, but we could also ask ourselves, is it also an ordinal variable? Like, can you somehow order very, somewhat, and not? And I would say yes, that very is stronger than somewhat, and somewhat is stronger than not. Nothing says it couldn't go not, somewhat, very, but the point is that there still could be some kind of ordering imposed there, so it is also an ordinal variable. Hours of sleep last night. Well, that's quantitative. And we tend to say things like, oh, I slept for 8 hours, when it really might have been you slept for 7 hours, 58 minutes, 33.76 seconds. So this is an example of a variable that's also continuous. Weights of adult women measured in pounds, that's also quantitative, and it's also continuous. Favorite color for an automobile, that is definitely categorical. You're only allowed to have one favorite. But there's no obvious order, and it says that red comes before blue. I mean, I guess you could kind of go with Roy-G Biff order, but really, this is not ordinal. For each of the following variables, indicate whether the variable is ordinal or continuous. Now, opinion about a new tax definitely is a categorical variable, but because there's only two categories, it's not obvious which order to impose. So this is actually neither. Bit of a trick question there. Heights of men in inches, definitely a quantitative variable, and as any value is possible within a certain interval, this is definitely continuous. And the within a certain interval thing is just saying that it isn't as if every single number is a possibility. For example, men can't be negative heights, and there probably is some lower threshold for the shortest possible man and some upper threshold for the tallest possible man. Grade in this class, well, that's definitely ordinal. There are categories, and you fall into one of those categories. You don't get an A- and a B+, you get one or the other, and you can definitely impose an order on those things. Now, we're often going to be talking about relationships between variables, and the words used in this text are explanatory variable and response variable. Now, the explanatory variable, which some other books call the independent variable, this is thought to influence or cause a response in that variable, as in the response variable. And that variable, the response variable, is sometimes referred to as the dependent variable. For example, we could take smoking as our explanatory variable, and we could ask, what is the rate at which people get lung cancer? And that's our response variable. We have to carefully design something to actually conclude that smoking caused lung cancer, but we might suspect that smoking is associated with lung cancer somehow. So for each pair of variables, specify which variable is the explanatory variable and which is the response. So the amount a person walks or runs per day and performance on a test of lung function. Well, in this case, I would say the explanatory variable is the amount of walking. Probably the response variable is the lung function. All right, feelings about importance of religion and age. So the religion probably isn't going to influence your age, so probably the other way around. The explanatory variable is the age, and the response variable is your feelings about religion. So let's begin by discussing how to summarize one or two categorical variables. Two different things we can do are find a frequency distribution and a relative frequency distribution, and here is what those are. A frequency distribution is a list of all categories and their frequencies. So for example, I could take this class and I could say, are you male or female? And I could tally up how many male students we have and how many female students we have. And I could make a graph, a bar graph, and on that graph would be a bar for how many female students and a bar for how many male students. And then the numbers would be how many students. A relative frequency distribution is very similar, but instead of giving the raw numbers, it gives proportions or percents. So this lists all categories with frequencies given as proportions or percents. So this table summarizes the frequency of seatbelt use while driving for the 2,530 12th grade participants in the 2003 Youth Risk Behavior Surveillance System. Here is a summary of their responses. So 105 students never wear a seatbelt, 248 say they rarely wear a seatbelt, 286 sometimes wear a seatbelt, 464 most times wear a seatbelt, and almost a large majority of the students, 1,427, say they always wear a seatbelt. So first question, what percent of the 12th grade students who drive say they always wear a seatbelt? Well, that is 1,427 say they always wear a seatbelt out of the total 2,530, which is approximately 0.564. So that's a proportion. In percent form, we multiply that by 100 or move the decimal over to the right 2 places and we get 56.4%. And unless otherwise specified, always give me at least one decimal place past the decimal there if you do indeed actually have a decimal value. If it comes up exactly 56, you can give me 56. What percent of the 12th grade students who drive say that they do not always wear a seatbelt? So that's everybody else. Well, since there were 1,427 people who always wear a seatbelt, adding up all of the rest of those, we see that there are 1,103 people who did not answer always out of the 2,530, which is approximately 0.436 or 43.6%. Note, you could have also found that by doing 100% minus the answer from part A that was 56.4%, as you're either always wearing your seatbelt or not always wearing your seatbelt. You get the same answer both ways. And let's find the percentage in each of the 5 response categories. So the percent. Well, 105 out of the 2,530 gives us 4.2%. You should double check these figures yourself. 248 out of the 2,530 gives us 9.8%. 286 out of that total gives us 11.3%. 464 out of the total is 18.3%. And the last one we already had, that was 56.4%. So next, let's draw a bar graph of the percentages that we found in part C. So draw 2 axes. On this lower axis, which is like the x-axis in lots of other math classes, we are going to put our categories. So we have never, rarely, sometimes, most times, and always. And on the vertical axis, we're going to have the percent. Let's say that's 10, 20, 30, 40, 50, 60. Now 4.2% said never, so we'll draw a little bar. That's approximately halfway to 10 for never. Rarely we had 9.8%, which is pretty darn close to 10%. So there's your never bar, rarely bar. Sometimes it's just a hair over 10%, so it'd be just a little bit taller. Most times 18.3%, so almost up to 20%. And always 56.4%, so that's about halfway between 50 and 60. And it seems to me that this would be a much better way to show somebody what your data said than just giving them that table. It's quite obvious from this picture that a lot of people fall into this always category, way more than most, sometimes, rarely, and never. So the 3 most common pictures used to represent categorical data are pie charts, histograms, which is kind of like what we just drew, and box plots. Now, pie charts and histograms can be used to describe the distribution of one categorical variable, and histograms and box plots also illustrate the location of the data and the spread. And if you have more than one group, you could compare them using side-by-side box plots. So we're going to do examples of each of those. So first, how to make a histogram. So the first thing you do is you define equally spaced discrete intervals encompassing all values of a variable in a sample. So I do running races. An example of making equally spaced intervals might be age groups. So you put everybody in 30 to 34, 35, 39, stuff like that. Then you count the number of observations in each interval, or the frequency. And the x-axis gets the endpoints of the intervals, and you draw bars with the heights equal to the frequency. So for example, I have a set of exam scores. Let's make a histogram of the data with boxes of width 10. So these are already ordered. So notice we only have 1 in the 50s, 2 in the 60s, 2 in the 70s, a bunch, 1, 2, 3, 4, 5, 6, 7 in the 80s, and 3 in the 90s. So it seems like a logical way to make boxes of width 10 is to do it by 50s, 60s, 70s, 80s, 90s. Okay, so draw your two axes. So if we have 50 to 59, on this axis we'll graph the number of occurrences. So how many fell in between 50 and 59? 1, 2, 3, 4, 5, 6, 7. So just 1. So the height is equal to the frequency of 1. In the 60 to 69 category, we had just 2. In the 70 to 79 category, we also had 2. In the 80 to 89 category, we had 7. 1, 2, 3, 4, 5, 6, 7. So there you go. And in the 90 to 99 category, we had just 3. So when your picture has this most common value, which is something called the mode, sort of appearing on the right-hand side, that's something that's called skewed to the left. You can kind of see that it's heaviest over here. So this is something called skewed left, and that refers to this little bit we call the tail, the lower end, that's on the left side. Had that bar been in the 60 to 69 category instead of the 80 to 89, we could have said that was skewed right. So, bell-shaped data is something that when you make a histogram, like what we just did, the picture looks something like this symmetric idea. And obviously if you have discrete bars, it's not going to be exact, but it has this bell-shaped general trend. And the kicker is it has this even reflecting symmetry. And this comes up with lots of things. Like if I looked at all the heights of the girls in this class, the data probably would come up to be quite bell-shaped, assuming the class was large enough. The mode is the most frequent value. And you can see that with bell-shaped data, that ends up to be the middle. Unimodal, you can see the uni, kind of like unicycle, one wheel. Unimodal has one mode. Nothing says that it has to be in the center. It could look something like this. But there's one highest value, but this is skew left, or it could be something like this, which is skewed to the right. Bimodal would be something that has two modes. Looks something like this. Sadly, that's something you observe a fair amount as a math teacher. Like say this is a B and this is about a D. You have lots of students that end up doing reasonably well and then lots of students who end up doing quite poorly. Unless you have a very, very, very large class, the data often looks to be a bit bimodal. Now, an important numerical summary that you will have to know how to find is something called a 5-number summary. And as the name suggests, there are 5 numbers in this summary. The first one is the median. The second and third are the maximum and minimum. And the fourth and fifth are something called the upper and lower quartiles. Now, nothing says that they have to be given in this order. It actually probably is best to give them in the following order. Give the minimum first, something called quartile 1 next, then the median, which roughly speaking is the middle value, then quartile 3, and finally give the maximum. And this will give the numbers in ascending order, as in from smallest to biggest. Now, roughly speaking, the median is the middle value. And once you have the middle value dividing stuff in half, if you look at your lower half only, the lower quartile is the middle of the values between the median, below the median. So you have your median that divides stuff in half. And if you look at this half only, the lower quartile is the median of that, or the middle of that. We call that Q1. And the upper quartile is the same thing except for above the median. So it's the middle of the values above the median. And another word for the maximum and minimum values, those are also called the extreme values. So we have median, Q3 is quartile 3, max up on top, min on the bottom. Now those are called quartiles for a reason. You can see the word quarter in there, and that's kind of what they roughly speaking do. They divide the data into quarters. This is the first 25% between the min and quartile 1. From the min up to the median, that's the first 50%. Up to quartile 3 is the first 75%. And to the max gets, of course, obviously the whole 100%. So we'll actually find a 5-number summary in the next lesson, but suppose for now I give you one. So the 5-number summary for the fastest speed driven by men, this was found doing some survey, is given by the following. The minimum was 55. Quartile 1 is 95. The median is 110. Quartile 3 is 120, and the maximum is 150. So first of all, what is the range of speed? So how spread out are these? So the way to find that range is you do the maximum minus the minimum. So that's 150 minus 55. So there is a range of 95 miles per hour. Now the interval containing the slowest 1/4 of speeds, as we just discussed, that's the min to quartile 1, or 55 to 95, which you could also give like this, if you felt like it. Now the middle 1/2, well, referring back to the previous discussion about the quartiles, the middle 1/2 is from quartile 1 to quartile 3, or 95 to 120. Now the last thing we're going to do is make something called a box plot to summarize this data. So here we just have a horizontal axis, and on that axis we're going to label that with all the possible speeds. So our lowest speed is 55, so let's just count by tens. 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150 is our highest. So those are speeds in miles per hour. Now we're going to draw lines at the min, quartile 1, the median, quartile 3, and the max. So the min is 55. Quartile 1 is 95. The median is 110. The upper quartile is 120, and the max is 150. And now the box goes around the middle 50%, so that's from quartile 1 to quartile 3. That's where Q1 was, that's where Q3 was. And then you draw lines that extend to the max and to the min. Now we'll learn a slightly more refined approach in the next lesson, because you also have to be careful that numbers aren't outliers or the box plot is drawn differently. But for now, this is what you can think about as a box plot. The box goes around that middle 50% with the median also drawn in there so you can see where that falls.